Hi everyone, it's Aryan from RigBetel Labs, and today I am excited to introduce you to a custom developed 6 DOF arm, a robotic arm that we created for a client. Stay tuned till the end to learn about all the amazing features of this arm. Similar to our previous video, a client approached us looking for a robotic arm for inspection purposes on their production line. For a previous client, we were able to procure a robotic arm from one of our vendors. If you haven't seen that video yet, be sure to check it out. I'll have a link somewhere here in the corner. In their use case, they wanted the arm to have a mode where the arm is able to navigate autonomously to the inspection points and provide us a close-up view of the area of interest. Also, a manual mode so that the user can remotely control the arm using a joystick. With this being the case, instead of purchasing a ready-made robotic arm, we proposed a custom-built solution to fit their budget and specified requirements. The client then shared their detailed requirements with us, and based on the needs, we showed them a couple of arms available in the market. They liked the design of Viper X300, a 6 DOF arm offered by Torsen Robotics. However, this robotic arm comes with a hefty price of $6,100 which translates to approximately 5.1 lakhs INR, excluding the import duties of course. This significantly was over the client's budget. So with the Viper X design in our minds, our team of engineers set to work on the designing and developing our own robotic arm. This arm can easily handle a high quality webcam and has a reach of around 750 mm, covering a total side-to-side span of 115 mm. To achieve a full 6 DOF motion, the robotic arm utilizes a combination of 8 servo motors. One 60 kg/cm servo motor for the base revolute joint, two 60 kg/cm servos working together as the shoulder joint, two 35 kg/cm servos working together as the elbow joint, one 35 kg/cm servo for the elbow rotation joint as well, one 25 kg/cm servo for the wrist up and down motion, and one 10 kg/cm servo for rotation of the wrist joint. On completion of the design, we presented it to the client and they were thrilled with it. While the parts were being manufactured, our ROS team began working on converting the CAD model into URDF and creating the MoveIt configuration files for the robotic arm. The ROS team was also successful in simulating the robotic arm's movement and functionality using Gazebo. Additionally, we implemented forward kinematics, allowing the users to move all the joints using sliders on graphical interface. With the implementation of MoveIt, we gained the flexibility to add inverse kinematics. Now, the users can simply move the blue marker in RViz to any desired location in the 3D workspace, and the robotic arm will automatically calculate the joint angles and the trajectories to reach that point. Finally, for enhanced user interaction, we compiled the entire inverse kinematic script onto this gamepad controller. This allows the users to have a manual mode to control the robotic arm's movement using joysticks. In this controller, one joystick was for up and down movement and left and right rotation, and the other for forward and backward movement of the camera.
Wait, you're probably wondering why I am here in this video. Well, currently we are experimenting with our content a lot right now, and I want you all to comment down and tell us what type of videos you want to watch next. Also, if you have been with us till here, I would insist you to like and share this video and also subscribe to our channel, as it takes a hell lot of efforts to create these type of videos. Now, let's get to the actual demonstration of this beautiful robotic arm. If you don't want to watch the whole demonstration, you can skip to the next part of the video. So here in the video, the user effortlessly slides through various joint angles, visualizing how the robot arm's position changes in the display below. Once they have found the perfect configuration, they can hit the plan and execute button. This initiates an autonomous path planning process, guiding the robot arms from its current position to the desired one. This is called forward kinematic control. Now, onto the inverse kinematic control. Users can directly specify where they want the robot arm by moving the blue marker in the 3D space. Just like the previous visualization, here as well, user can see the current arm state in grey and expected position in orange once it reaches the goal. This control method is particularly effective for precise straight translational movements along the X, Y and Z axis, with the algorithm calculating the necessary joint angles and acceleration for seamless execution. After positioning the robotic arm to satisfaction, users can press the plan and execute to autonomously navigate the robot arm to the designated spot. Our third method of control involves a joystick, used in real deployment scenarios. Users can manipulate the end effector position by moving the joystick up or down, left or right, forward or backward. What's remarkable is that users don't need to worry about the different joint angles of each joint of robot arm. The algorithm processes that autonomously. All you have to do is to guide the end effector to the desired location. Additionally, the robot demonstrates real-time joint visualization through RViz software in ROS.
It's worth noting that all the control features were initially tested and refined in ROS simulation model in Gazebo by our talented ROS team. This strategic approach ensures a smooth transition from simulation to the real robot, making the entire process remarkably streamlined.
These are just some of the amazing features of the robotic arms that we created for our client. If you are also interested in us having developed custom robotic arms, AMRs, UGVs, AGVs or any other ROS compatible robots, you can reach out to us at info@RigBetelLabs.com. We can then understand your requirements and provide you with the best of solutions. So that's all for this video. This is Aryan signing off and see you in the next video.